Welcome back. Today we covered trigonometric identities. Notice that project 7 was assigned last class, so it will be due a few classes from now, and also quiz number 7 is happening next class as well. Okay, let's take a look at the notes. In this section, we introduce some important trig identities. An identity is an equation that is true for all values of the variable. Is x squared equals 9 an identity? How about x times x cubed equals x to the 4th? Okay, again, an identity is something, it's an equation that's true for all values of the variable. Now, for example, this equation right here is true for x equals 3, and it's also true for x equals negative 3, but is it true for all values of x? Is it true for x equals 2 or 17 or negative pi? The answer is no. An identity is supposed to be true for all values of x. So an identity isn't an equation to be solved and find the values of x that make it work. But an identity is something that's supposed to be true all the time. It's not an equation to be solved. But this one over here, x times x cubed, well, we know how to combine those two things, and we know that that's equal to x to the 4th for all x. So you can plug in x equals 2 or 17 or negative pi, and that equation will be true. And so this is an identity. So a real big difference between an equation. You guys have spent much time solving equations, and you'll find the value or values of the variable that makes the equation true, versus an identity, which is something that's true for all values of x. Number 2, how can we check to see if an equation could be an identity? We can do this graphically. Let's identify which of these could be identities by graphing them on our calculators. So part A, x plus 3 squared equals x squared plus 9. So you can look at that and decide whether or not you think that might be true for all values of x. I'm hoping you have a good sense as to whether or not that's true for all values of x. But regardless of whether or not you have a good sense about that one, we can check by using the calculator, and we can plug in y equals the left-hand side here. And then down here in y2, we can plug in the right-hand side. And just so we can really see these things apart, I'm going to hit enter over here. I've got the cursor on the far left, hit enter, and that line gets thicker. So the second one will be thicker. So if this is an identity, then these two graphs should look exactly the same. And so whatever the first one is, it will just get retraced thicker on the second one. But if it's not an identity, these two graphs are not going to be exactly the same. So zoom 6 is probably fine for this one. So there's the first graph, there's the second graph, or part of it anyway, and it is definitely not the same graph. So this is certainly not an identity. It is not true. What if we look over here? Square root of x squared plus 9 equals x plus 3. It seems reasonable. We just distribute that square root. X squared becomes x, 9 becomes 3. Again, I'm hoping you have some sense about whether or not this thing is true. Let's be a little bit efficient. So I'll type in square root of x squared plus 9 there, and then x plus 3 here. And with a graph, x plus 3 is a line. Square root of x squared plus 9 is definitely not a line. So it's not true. I mean, it's true for certain values of x. It looks like it's true here at x equals 0 because that's where the graphs hit each other. But it's definitely not the same graph. So that is not an identity. Okay, now let's look at this crazy one here. 1 over 1 plus cosine x plus 1 over 1 minus cosine x equals 2 cosecant squared x. Okay, I'm hoping you don't have any intuition about this one. There's no reason to know whether or not these two things happen to be equal all the time. So this is where the calculator will help us when we have no intuition. So we will carefully type this thing in. And that's y1 on the left, and then over here, 2 cosecant squared. Now we don't have a cosecant button, so what we're going to have to do is recognize that cosecant is really 1 divided by one of the trig buttons that we do have. That's 1 divided by sine. I forget my division symbol. Okay, but it was supposed to be squared, so we'll square this thing. If you really want to be safe, you can put parentheses around sine x. I think that it's okay to not have them. And again, I'll make the second one thick. So we're going to graph the first one. No idea what it's going to look like. Okay, it's that. And then once that finishes, it will graph the second one. And if we get a different looking graph, then it's not an identity. But if we get something that traces out exactly the same graph, or at least appears to, that's pretty compelling evidence that we're looking at an identity. So this one is a no, not an identity, different graphs. That's a no, not an identity. This one is yes, the two graphs looked exactly the same. All right, the mathematician in me says, well, but can't know it's exactly the same just looking at the picture, but probably yes. 3, let's prove the identity from the list above. I'll give you some strategies on proving identities in a bit. Okay, so we're going to take this left-hand side here, 1 over 1 plus cosine x, 1 over 1 minus cosine x, and then the right-hand side, 2 cosecant squared. And normally this is an equal sign in between. I'm not going to put an equal sign in between. I'm going to put a big red line straight down the middle here. And that big red line is supposed to cue you into the fact that you don't have an equation, so you can't play with this thing as if it were an equation. You have two expressions that you are hoping you can relate to each other. You're hoping you can make them look exactly the same at some point. But under no circumstances are you allowed to treat this thing like an equation where you can say add 5 to both sides or multiply both sides by 1 plus cosine of x. You can't. You don't have an equation to do anything with both sides of. So we completely separate these two expressions and then we manipulate them separately and hope that at some point they look the same. Okay, one technique is to start with the thing that's more complicated. That looks like the left-hand side. I have two fractions added up. It feels like we're going to want to go for a common denominator here. So let's go ahead and convert these guys into something with a common denominator. So there's 1 over 1 plus cosine x, just copied. And there's the second fraction, and what we're going to do is multiply the bottom here by 1 minus cosine x, and multiply the bottom here by 1 plus cosine x. And in doing that, the two denominators of these fractions are exactly the same. So that's my lowest common denominator. But then you got to pay for it, so you multiply up here by whatever you multiplied downstairs, and then up here by whatever you multiplied downstairs in this fraction. And then we'll mush these things together. So I'll put a plus sign here. I now have one big fraction. There's no reason to distribute there, but we might anyway, I don't know. For right now, it looks like that. And upstairs, I'll just copy. I guess we can distribute the ones. So 1 minus cosine x plus 1 plus cosine x. Okay, and running out of space a little bit, but something nice happens upstairs. The cosine x's cancel, and we just get 2 divided by. And I don't really know what to do here, so I'm just going to pause there on that one. Gone as far as I can. I'm tempted to just copy the bottom, but maybe foiling would help. Okay, here's a 2 cosecant squared x. All right, well, the first thing I want to say is I really like the 2 that's in front there, because we just got a 2 on the top of this fraction. Okay, cosecant somehow is supposed to turn into something with the cosines in it. How about we just go to the definition of cosecant, well, not definition, but one of our facts about cosecant, and that was that cosecant is really 1 over one of the other trig functions. It's 1 over sine, and that thing right there is supposed to be squared. I don't really know where else to go with that one, so let's come back here and say, well, they're kind of starting to look similar. I say they, I'm thinking about this thing right here and what we're getting down here, but I see that it's sine squared down there, and currently it's cosines, so maybe distributing will help. So let's FOIL out the bottom. This is a special case. The outers and inners cancel, and we just get 1 minus cosine of x squared. But that 1 minus cosine of x squared, I'm hoping, jogs some memory for you. 1 minus cosine x squared is part of one of the Pythagorean identities. So I'll just write a fact over here that we saw that sine squared of x plus cosine squared of x is always equal to 1, no matter what angle you plug in for x. So then if I wanted to get 1 minus cosine out of this thing, 1 minus cosine squared, I could subtract cosine squared from both sides and say that sine squared is really 1 minus cosine squared. And that's the missing link here, because 1 minus cosine squared is what I have. I could then replace it with sine squared because it's equal. And then I think we win, because this one becomes 2 over sine squared of x. And then coming back here, mushing these things together into one fraction, this is really 2 over sine squared of x. And so then I'll just circle in green this thing right here matches this thing over here. And so kind of working our way up, we know that this guy is equal to each one of these things going all the way up to the top. In fact, going all the way to the top here. And we know this one is equal to everything going up to the top here, which means that this guy and this guy must equal each other. Okay, so let's take a look at number 4, a list of some important identities. And we'll see proofs of many of these on the very next page. The double angle identities, for example, sine of 2 theta is equal to 2 times sine theta times cosine theta. I can maybe convince you that that could be true by looking at the calculator here. So instead of graphing both sides, I'll do something that's not quite as compelling, but still pretty compelling. If I wanted to do, for example, sine of 2 times 25, so I'm really looking at the sine of 50 degrees, so it's some number. There it is. That is not the sine of 50 degrees. I didn't follow my own rule. Need to make sure we're in the right mode. So let's try again. Oh, sine of 50 degrees is that compared to, so now theta was 25. So I'm just going to copy this guy, but put theta equals 25. 2 sine 25 times cosine of 25. And if this identity is actually an identity, then these two numbers should be exactly the same. That's not a proof, because just because it was true for theta equals 25 doesn't mean it's true for all theta, but it's pretty compelling, right? It would be a pretty major coincidence if it was true here, but different elsewhere. That's a double angle identity because it involves sine of double some angle. There are 3 double angle identities for cosine. The first one is what I think of as the main one. Cosine theta is cosine squared minus sine squared. And then there are 2 others. I said cosine theta. I should have said cosine 2 theta. And then cosine 2 theta is 2 cosine squared theta minus 1. And then one more down there you can read. Then we have these 3 symmetry identities. By the way, these are the double angle identities for sine and cosine. Just as well, there are double angle identities for the other trig functions, but these are the ones that we'll be focusing on. The symmetry identities. If you ever see cosine of negative theta, you can just write cosine of theta. Sine of negative theta, however, isn't the same as sine of theta. It's actually negative sine of theta. Same is true for tangent negative theta. It's negative tangent theta. And then the translation identities down here, cosine theta minus pi over 2 is really the same as sine theta. And then sine of theta plus pi over 2 is the same as cosine theta. So on the next page, like I said, we'll see proofs of a bunch of these things. Number 5, we will prove the first 2 double angle identities next class. If we believe cosine 2 theta equals cosine squared theta minus sine squared theta, we can prove the 2 other identities involving cosine 2 theta. So to be honest, there's no reason you should believe this at this moment, but if you can just bear with me and wait until next class when I will prove to you that this equation is true, then we can prove these other 2 ones right now, and it's pretty easy to do so. So let's give it a shot. Here's what we're going to do. We're going to use the fact, again, that sine squared theta plus cosine squared theta is 1. That's our Pythagorean identity. And so, for example, if I wanted to, I could solve this equation for sine squared theta. We did this on the previous page and get 1 minus cosine squared theta. And just as well, we could solve the first equation for cosine squared theta and get 1 minus sine squared theta. So 2 facts that we're going to use. So using this equation, which we're assuming temporarily, cosine 2 theta equals, well, instead of this cosine squared theta minus sine squared theta, I'll copy the minus sine squared theta, but I'm going to change the cosine squared theta using this identity right here. And apparently cosine squared is really 1 minus sine squared. So simplifying the right-hand side, we get cosine 2 theta equals 1 minus, and then combine those two sine squared thetas. And lo and behold, we have a brand new identity. Cosine 2 theta is 1 minus 2 sine squared. And that's one of the ones on the previous page. And then we'll do it another color. Again, copying this one that we're temporarily believing. Cosine 2 theta equals cosine squared theta minus, but now instead of sine squared theta, I'm going to put 1 minus cosine squared theta. 1 minus cosine squared theta. And therefore, cosine of 2 theta is equal to, combining like terms here, let's see, the minus cosine squared really becomes positive cosine squared. So we have 2 cosine squared theta minus 1. And that right there is another one of the identities you can see on the previous page. So if you have the first cosine of 2 theta identity, if you believe that one, then the other two follow very easily. 6, the symmetry identities follow from our unit circle definition of the trig functions. So we know that we've got this standard looking picture here that if you have the angle theta inside of here, then, and you're on the unit circles, that's a 1, then the x-coordinate of this point is cosine theta and the y-coordinate is sine theta. So that's something we've known for a while now. And the symmetry identities ask us to think about finding cosine of negative theta and sine of negative theta and tangent of negative theta. Okay, well, if theta is as it's drawn in this picture, then negative theta must be down here. So we'll just ballpark negative theta in here. And that leads us to a point that is down here. And what's true about this point compared to the coordinates that we had up above? Well, the x-coordinate that we had up above is exactly the same. So that x is still x. And the y-coordinate, let's do this one in another color. The y-coordinate over here must be the same as this y-coordinate, except it's got to be the negative because it's down below. So this is really x and then the opposite of whatever the y is. So in this case, it's we said x was cosine theta, so that's fine, comma, but then instead of y, it's got to be negative y, which is negative sine of theta. So it's the same point that we had. The x stays exactly the same. The y has to change and become negative. So in terms of filling in these identities over here, cosine of negative theta, well, we know that cosine of negative theta is whatever the x-coordinate is at this point right here. And apparently the x is cosine of theta. But if you want to do sine of negative theta, then we know that sine of negative theta is the y-coordinate at this point right here. And the y-coordinate is actually negative sine theta. So sine negative theta is negative sine theta. And then tangent negative theta, well, we know tangent is defined to be the tangent of some angle is the y divided by the x. But in this case, the y is actually the negative of what it used to be. So it's just the opposite of whatever we got before. So instead of y over x being sine over cosine, it's now negative sine over cosine, which is just the negative of tangent theta. That last one is a little bit trickier to see than the other two, so feel free to slow down the video here and think about that a little bit more if you didn't quite get it. 7, the translation identities follow from the graphs of sine and cosine. Okay, so let's go back to the previous page and just grab those two translation identities. So down here at the bottom, cosine of theta minus pi over 2 and sine of theta plus pi over 2. So let's write that. Okay, so thinking about the cosine graph, which is this one up here at the top, we say it starts at the top and then goes down, so that's cosine theta. Well, what happens to a graph in general when you subtract inside of the function? So this graph should just go to the right, and it should go to the right by pi over 2 of whatever it was. So if that's pi, then this must be pi over 2. So we're going to take each of these points up here, and we're going to move them pi over 2 to the right. So this point goes pi over 2 to the right, this point goes pi over 2 to the right. This one goes pi over 2 to the right. And this one, pi over 2 to the right. And just one more for good measure. Let's take this point and send it pi over 2 to the right. And so if I connect those 5 dots that I just drew, then I should get a very familiar looking graph. It sure looks an awful lot like sine. So cosine of theta minus pi over 2 is just exactly the same as sine of theta. And so if you have cosine and you shift it pi over 2 to the right to land on sine, then if you start with sine and shift it pi over 2 to the left, which is exactly what this thing says, then sure enough, we should get cosine. So again, feel free to slow down or just pause the video here. You can plot some points, take each of these guys and shift them pi over 2 to the left, which is what this says to do, and convince yourself that it actually looks like cosine. Next page. Our basic strategy for proving identities is to simplify or modify both sides of the equation so that they look the same. Here are some things to try. A, use known identities. For example, replacing sine of 2x with 2 sine x cosine x, or sine squared x with 1 minus cosine squared x. So we've seen both of those equations today, although we had them with thetas instead of x's. But with a little bit of experience, you start to recognize some of these things that you've seen before, and then you can just replace. Anytime you see a sine of 2x, you can just change it right away to 2 sine x cosine x, and that might help. B, rewrite everything in terms of sine and cosine, and then here in the parentheses, I've got the other 4 trig functions written in terms of sine and cosine. C, work backwards or in both directions. D, find common denominators for fractions. We did that on the first one. E, factor, and F, don't be discouraged if your first attempt fails. Try something else. Identities is really not something that you're supposed to just get the first time through every time. So failure is inevitable, certainly for these identities. Okay, number 9, let's prove an identity together, and then you'll do a bunch in the activity. We might do this one in a couple different ways. Okay, so I will copy both sides separately, and I'll put that big line in between so that I make sure I don't cross that line. So big red line going right through the middle. Okay, so one thing we can do on the left-hand side is split this up into 2 fractions because I have one denominator with subtraction upstairs. So convince yourself that this is really the same as 1 over cosine minus cosine over cosine. So that's just a fact about fractions, has nothing to do with trig. And then we can start rewriting a little bit. 1 over cosine, well, that's one of our other trig functions. It's up here in the parentheses if you don't know it, but it's right here. 1 over cosine is really secant theta. And secant theta is kind of the first promising thing I've written here because there are secant thetas, or at least there's one secant theta right there. So that's good, and then it's minus 1. So I get secant theta minus 1, and I don't feel like there's really another natural place to go from there. So maybe we can continue that one later, but let's pick up and see if we can do anything with this identity on the right, or with the expression on the right-hand side. Tan squared over secant theta plus 1. Okay, tan squared is part of one of our Pythagorean identities. And so we saw, well, we don't have it written here, but we know the sine squared plus cosine squared is 1. So we might not know this one as well, but we need to have it available to us. So what does it say? It says that tan squared theta plus 1 is really secant squared theta. And so if I just want the tan squared theta, then I'll subtract that 1 from both sides. And so we can replace the top with secant squared theta minus 1. And that's divided by secant theta plus 1. I just want to highlight again, you cannot cross this red line. And so even though it looks like an equation with 2 fractions, and you might just be programmed to cross multiply every time you see an equation with 2 fractions, you can't. It's not an equation that we know is true yet. So you can't do anything to both sides of the equation. You got to deal with them separately like we are here. Okay, please, please, please don't try canceling secant here and here, or canceling the 1s. What we need to do is factor the top. So let's factor the top. The top factors, it looks like this. At the moment, the top is really like an a squared minus b squared. So that's really secant theta minus 1 times secant theta plus 1. Pause the video if you don't believe that, if you don't see that. Go ahead and FOIL these two things together and make sure you get what we had upstairs. I'll copy the bottom. And then something really good happens. Now that we've factored, we're ready to cancel. Secant theta plus 1 is a copy of what's down here. And lo and behold, I get exactly secant theta minus 1. And this one just kind of feels like it fell in my lap. I didn't really see that that was going to happen, but secant theta minus 1 is now the same on both sides of my red line. So we've proven our identity. Okay, so that is one way to do this problem. I'll put a big blue line here in the middle and present an alternative way. Okay, so another option is to change everything into sines and cosines right away. Every time you see any trig function other than sine and cosine, change it to sines and cosines. So I will copy the two sides, and again, make sure we keep them separated with a big red line. Do not cross that line. Okay, so the left-hand side is already only sines and cosines, so the right-hand side requires work. So tangent we know is sine over cosine. So this tan squared is really sine over cosine, the whole thing squared, divided by. Secant is really 1 over cosine. And then there's a plus 1. Okay, so let's go ahead and clean up this big mess of a fraction. Upstairs, that squared comes in and hits both top and bottom, so we get sine squared theta over cosine squared theta, divided by, I'm going to go ahead and get a common denominator down here. It looks like cosine of theta will be the winner. So let's make a common denominator. We'll do this in one shot here. So cosine theta there, it was a 1 plus, and then this guy, again, pause the video if you don't see what happened, but all we did was make this thing right here cosine over cosine. So there's the cosine over cosine. Okay, and now we've got a compound fraction. That is a fraction within a fraction. Two different fractions within the big fraction. And what I'd like to do here is clear out the denominators that I have in these two fractions. So I don't like this and I don't like this. So I'm going to multiply the top and the bottom by exactly the right thing that will cancel both of these guys. And the right thing is cosine squared. So let's multiply up here by cosine squared. And then down here by cosine squared. So times that whole thing, and times this whole thing, and then the point of that was right away to cancel. Cosine squared cancels here. One of these cosines cancels with that one, and there's still one left over. Okay, so what do we have left now? Upstairs, it's just sine squared. That's good. That's simpler than what we've had before. Divide by. Downstairs, I have a cosine, which I will go ahead and distribute. Cosine theta plus cosine squared theta. In fact, distributing that, I'm not convinced that that was such a great idea. So let's not do that. Generally, distributing on the bottom is not such a great idea. Okay, so I'll just copy it. Cosine theta times 1 plus cosine theta. Okay, I don't really know how much progress I made. I know it's simpler than it was before, and it's got only sines and cosines, which is good because the left-hand side had only sines and cosines. Left-hand side is supposed to eventually look like this thing, 1 minus cosine over cosine. So let's take a look at what we have. All right, at the top, this one is supposed to be a 1 minus cosine. This one down here is just cosine, so I like that guy. And in fact, that's why I decided to not distribute there, because I said, oh, wait a minute, I want a cosine down there. So, but I don't like this thing here. So let's see, sine squared theta. Well, we see sine squared, and we could immediately replace it using one of our Pythagorean identities. Sine squared is really the same as 1 minus cosine squared. And now I feel like we're almost there. We can factor that 1 minus cosine squared, and then I think good things will happen. So upstairs again, it looks like an a minus b times an a plus b. And then I'll copy the bottom, still not distributing. And then hooray, 1 plus cosine theta is the same on top and bottom. So we can cancel, and we just get 1 minus cosine theta divided by cosine theta, which I will circle, because that is exactly the same as, well, it's exactly the same as what we started with on the left-hand side. So we've proven the identity a second time. So sometimes, like in here, you end up working with each of the two sides separately, and you just go as far as you can, and you hope that at the end you have two things that are exactly the same. Sometimes you don't go anywhere with one side, and you just do all of the work on the other side. But again, all you need is for the two sides to match up at some point. Okay, which one of these two was easier? Well, it sure felt like the first technique was a little bit less work. And so I wanted to show you what I meant by change everything to sine and cosine. Some students just like that. It's an easy enough rule to apply, and then maybe you're in more familiar territory because you don't have to deal with any of the more exotic trig functions, you know, secant and cosecant, cotangent. But the bad news is it might just be more work for you. And we saw a lot of work on the right-hand side using the sines and cosines only. Okay, number 10, note there is a trig identities reference sheet on Moodle that you can use on the quiz, and maybe have that available to you while you're working on the homework. And the activity follows, and go ahead and give that a good shot before you look for the video.